Hello again, everybody. So I'm still in my little room, but I have a decent view of a nice creek and marsh. Today we're going to be talking all about kinetic theory of matter. This is not a particularly long lecture. A lot of it is just going to be picking apart what different parts of an equation means, just so that it's not so abstract. Um, so We're going to talk about kinetic theory of gases, this idea of describing gases in terms of the motion of its particles. And we're going to look at the relationship of that motion in terms of temperature of a gas, pressure, the volume of this sample, and how fast the particles are moving. And then we're going to look a little bit at kinetic energy. Energy is oftentimes used to describe a lot of things. It's a really useful tool. So we're looking at the average kinetic energy of a gas particle when it is hot or cold at a specific temperature. We're going to be looking at a constant called Boltzmann's constant, and really what it represents and why we care about it. Well, if we're talking about kinetic energy, it's probably not so weird. We can also talk about the velocity of a gas particle at depending on how hot or cold it is. I've posted video clips in Schoology. There were 3 that I really would like you to look at on your own. There is 1 set of practice problems for Unit 7, and they are posted. There should be time in class today for you to be able to work together and have some conversation about it. Thursday is going to be this kind of altered version of the quiz. I have to make an alteration just given the fact that I haven't been able to be there, and I don't want you to be punished for it. So you can be working in groups of up to 3. And then Unit 7 is real short. It's just this week, so we'll wrap it up on Friday. When you take the quiz, immediately after, there will be solutions available. I really hope I'm there. But if not, solutions will still be made available, and you can look at what happened. And then we have our second of 2 units on thermodynamics to finish off before winter break. Here's the same calendar I showed you before, so nothing new here. So again, there's the 3 videos on the left. I really would like you to take what's in the end 24 minutes on your own to look at them, and the other 2, if you got time. As I had mentioned, today is going to be really talking about this kinetic theory of matter, and specifically with a gas. So we're looking at this tiny, tiny level and what's going on down there, and then we're going to look at what that tiny, tiny motion at the level of atoms and molecules, what that looks like at the scale, macroscopic level, the scale that we can actually observe directly, because we can't, put a little radar gun on an atom, at least not yet. So previously, we had already started to talk about this kinetic theory of gases. So a bit of this is reminder, but a little review doesn't hurt. We had assumptions when we made this model. One is that we are dealing with a large number of particles, so that we can view this all statistically. And that essentially all the particles take up, the particles themselves have a tiny volume compared to how big their container is. So they're spread out. They obey Newton's laws. First law, object in motion stays in motion in a straight line unless acted upon by an outside unbalanced force, second law, Fun equals ma, and third law, for every action, there's a reaction. So they obey these laws, but they're moving randomly. So we don't have all the gas particles moving one way, just random scattered motion. The only way particles interact is by collisions. So no gravity, no magnetism, no electricity. And we got even more specific, saying that these are elastic collisions. So we're not even having to worry about any kinetic energy that's lost when gas hits other gas particles or when it hits the walls of its container. Perfectly bouncy collision. And then that just, we don't have different types of gases, most specifically different masses. So every single particle, same size, same mass. So, molecular model. This just means that we're describing the pressure that gas exerts on the walls of a container, like a balloon, in terms of atoms and molecules. So this really does go just back down to kinetic theory. All the little bits and pieces are moving. So they bang into the walls, they exert a force on the walls of the container. So we're saying that the pressure of a gas, so how hard the gas pushes out on the wall of its containers, is proportional to the number of molecules per unit volume, so density. If you have more molecules, there are more collisions that are possible. You just got more stuff that's available to run in the wall. And every single impact on that wall wants to push it out more. More impacts, more pressure. And then it also relates to the kinetic energy of the molecule, essentially how fast it's going. You run something into a wall at low speed, it pushes on it a little. Run it into a wall at high speed, it pushes on it a lot. So we describe it using this. It's Pivnert, and then we're also looking at this middle term, which is talking about the number of particles. That's big N. Little n is number of moles. The mass of the particles. Okay, so that would seem to make a difference. You'd have more pressure if you had really big, massive things running into the wall of a container. And then how fast they're moving. Again, if you have something moving really fast, it'll hit a wall hard, and it will exert a bigger outward force. And we're going to pick this thing apart a little bit. That's our main focus today. So there it is again. So let's talk about the fact that there is a 1/3 in there. The reason that we are dividing by 3, why there's a 1/3, is because this equation as it's written is only describing motion of a particle in one axis, so like the x-axis. So that's 1/3 of the directions that you can be moving, x, y, and z. This term right here, it's related to the energy that a particle has, and it imparts to the wall of a container. We're going to pick that apart more too. Okay, so this isn't in the equation, but we're going to look on this. Turns out this tells you the force that each individual particle exerts on the wall of its container. What is that L? Well, L is the distance between the sides of the container. If you just look at that term in the upper right blue box, even if we didn't know what L means, when L gets big, whatever number we're calculating gets small. So think of it this way. If the sides of a container are really far apart, it's a really big container, a particle to go from one wall to the other takes more time. It's spending less of its time hitting a wall and more of its time in transit. So that's what that L is. And the 1/3 is that it averages out all 3 axes. That's why there's a 1/3. Here's an interesting fact that isn't just a fun fact. You may have never come across this, but pressure is actually a measurement of energy per volume. Let's see how that works out. Okay, pressure. The definition of pressure is how much force is being exerted on a surface, and how much it gets spread out. So if you have a lot of force that's concentrated in a tiny area, like if you were to take a pen or pencil and put the pointy end on a piece of paper, it's going to be a lot of pressure. Now, you don't even necessarily have to exert a lot of force, but it's a tiny little area, and there'll be enough pressure to punch a hole in that paper. So we measure force in newtons, and we measure surface areas in meters squared. Okay. Well, this is at first just going to look like I'm just deciding to do a little bit of algebra for no good reason. Let's decide to multiply both the numerator and the denominator, both the top and the bottom, by meters. Well, that's totally legal mathematically. Great. So we we multiplied both by m. Those are equivalent. Wait a second. M cubed, well, if m squared is area, m cubed is something else. I think you know what that is. And I'll bet you some of you remember what a Newton times a meter is. Starts with a J. That's right, it's a joule. So a Newton per meter squared, what we measure pressure in, can also be measured in joules per meter cubed. And the way that I think is really useful to think of it, because when you're talking about energy, it's like, what's the energy? Think of it in terms of a spring. If you have a really compressed spring, there's going to be a bunch of energy stored in that thing, a form of potential energy. And you think about gas, if you were to take a balloon and you squish it down, you're going to decrease the area. You're going to have a lot of force per unit area exerted on that wall. There's going to be a lot. Think of that gas as just a three-dimensional spring. As soon as we let go, it wants to release that stored energy. So the energy we're talking about really is a form of potential energy. Okay, let's go back to this. And we just remind ourselves that big N is number of particles, little n is number of moles. Okay, pressure times volume tells us the energy contained in a sample of gas. Pressure told us energy per volume. Well, if you multiply energy per volume times volume, you get energy. So that's why PV tells you the amount of energy. Think of it very much like a spring. How much energy is stored in a gas? So again, big N, number of particles, little n, number of moles. It's just two different ways of keeping track of how many little bits and pieces we have racing around inside of a container. You probably remember Avogadro's number. Yep. So we can just divide both sides of that first equation by little n. So it gets rid of the little n on the right side, and it turns the term on the left into Avogadro's number. Okay. Let's just look at that. All right, I'm going to get all fancy pants here, and I'm going to divide both sides by NA. Would you look at that? That's some pretty tricky stuff. Okay. Uh-oh. Gonna go for a fancier move. Take a look at that. Well, let's talk about this KB. So we got rid of the R, universal gas constant, divided by Avogadro's number. And that gave us this thing we call Boltzmann's constant. Wow, it's a constant. It's named after a guy named Ludwig Boltzmann. Did a lot of work in thermodynamics. All right, so let's look at this. I'm going somewhere with this, I promise. Now I'm going to multiply both sides by 3. All right, we're just having fun doing algebra. And now I'm going to multiply both sides by a half. Think about why I would take this equation and multiply both sides by half. What physical meaning does that give us? Wait a second, 1/2 mv squared. I know what that is. That's kinetic energy. So 3/2 times this thing we call Boltzmann's constant times temperature in Kelvin tells us the average kinetic energy of a gas particle. And translational just means that it is in a straight line, as opposed to it like vibrating in place or spinning or something like that. It's the kind of kinetic energy we've talked about a lot. Car drives down a road, you take 1/2 times its mass times velocity squared, and you know it's kinetic energy. Here is what Boltzmann's constant is as a number. All right. So, great, it's a number. Here's the thing. Why do we even care about Boltzmann's constant? It's just a constant. We multiply things by constants. This is an interesting one because it links two things. So it links the energy of one little particle, so one atom or one tiny little molecule. So this is something that's at the way, way, way tiny scale, and it links that to something we can directly observe, temperature. So this is important because it gives this connection between what we really can't observe directly, certainly not easily, and something we can easily measure with a cheap piece of equipment. So that's a really interesting bridge. That's why we care about Boltzmann's constant. And you look at the equation, it's pretty simple. We have a constant. The only thing we're going to be able to change is temperature. So this is pretty straightforward. Okay. Velocity of a gas particle. This is what's referred to as a root mean squared value. I'm not going to get into exactly what that means. It's just a way to find it's a very typical way to find an average. So big M, molar mass, easily looked up on a periodic table or the interwebs. Turns out the molar mass of oxygen, a molecule of oxygen, so O2, is that if you have 1 mole of it, it's going to be 32 grams, 0.032 kilograms. 32 grams, that's something you could detect easily in your hand. Someone put a 32-gram mass in your hand, you'd know it's there. Wouldn't cause you any problems, but you'd know you're holding something. Universal gas constant. So if we know this molar mass of oxygen in the form we're actually going to find it, because we don't find just O running around. It's always going to be O2 under any normal circumstances. And we got this constant, this universal gas constant that relates energy of a particle with the temperature and how many moles of a gas we have. How fast is a molecule of oxygen moving around at room temperature, which is 300 Kelvin. So I would like you to pause the video here for about 2 minutes, maybe even less, so you could just give it a calculation. So please pause now. And we are back. So that probably didn't take 2 minutes. So at room temperature, the oxygen that's around you, which is not the majority of the gas around you, that's nitrogen, but still, we know we have oxygen because we are alive. That gas particle of oxygen, that molecule of oxygen is moving over 1,000 miles an hour, and you're just getting hit with them constantly, unbelievable amounts of times in a second. Turns out those little impacts we like because we have dissolved gas in our blood, and that exerts an outward pressure. So we really like the fact that the gas on the outside of us is pushing on us inward. So we get a balance, because if we just have nothing but outward gas pressure from inside of us, we would be like a grape in a microwave, and that would be unpleasant. Okay, so we were really just kind of picking apart how we think about little bits and pieces, atoms and molecules moving, and how that relates to temperature and speed. That is what I've got today. You should have plenty of time to sit down with each other, make wise use of your time, and work on practice problem 7.1. All right, do me proud. I hope to see you soon. Bye-bye.